All right, so I want to talk about the limit theorem. Some of these we mentioned kind of in passing, some of the concepts yesterday, but I want to address them a little more formally here, but then also start to put them together and kind of see how they're useful. We looked yesterday at the fact that if we have a polynomial, you can find the limit as x approaches any value in a polynomial simply by evaluating the polynomial at that point. And what property of a polynomial allowed us to do that? Polynomials are continuous, okay? They're continuous, all right? So because it's continuous, we were able to simply evaluate. A constant function. A constant function is just a horizontal line, right? And lines are polynomials of degree 1, right? Or actually, I'm sorry, degree 0. So since it's a form of a polynomial, you could evaluate it as well, and you know every value on a horizontal line is the same. So the limit of a constant is simply that constant. All right? The value never changes. This next one may not be quite as obvious here, but let's take a look at this. The limit of a constant multiple of a function is the number times the limit of the function. All right, so you'll notice here we have this constant b being multiplied by some function. We can simply take b outside the limit, find the limit of the function itself, and then multiply that limit by b. Okay? You can actually see this in, say, a polynomial. Let's say we had the limit as x approaches 5 of, say, a 4x squared. Well, you already know, since that's a polynomial, 4x squared, you can just evaluate it at 5. So you know that it would be 4 times 25, which is 100. We could also pull the 4 out in front and find the limit of x squared.
But we don't have to do that, right?
You don't have to. I'm showing it to you here with a simple function because you're going to see it later with, like, you know, if we wanted to find the limit as x approached 5 pi over 6 of a 10 sine of x, we can pull the 10 out and just look at our sine curve. Okay? Either way, though, in this case, we're going to get 4 times 25 is 100. Okay? So those are some basic theorems we've got there. Let's look at one other one. Just running through these kind of quickly. The limit of a sum of functions. Okay? Here we see we're taking the limit of this function here that's a little bit more complex. But I notice that the first two terms here make up a quadratic function. All right? So what I can actually do with this is I could separate this, the limit as x approaches 5 of x squared plus 3x, plus the limit as x approaches 5 of the square root of x over the square root of x minus 1. Now, as you guys get more comfortable with this is the thing that you're going to be doing in your head. You wouldn't necessarily write this out as two separate limits, but this is what's going on in your head. You're recognizing, hey, here's a part that I can obviously just evaluate. Okay? It's a polynomial. So I plug in 5, I get 25 plus 15, and that's 40. So now I've got to figure out what this other limit is. Okay? It's a way of isolating the more complicated part so we can just handle that on its own after we've already dealt with the easy parts. Okay? So at this point, we need to remember a little rule that we looked at yesterday, and that was when are you allowed to simply evaluate a function to find the limit?
When it's continuous.
When it's continuous, where?
Around the limit.
On the limit.
Around the limit, yeah. Around the limit. If it's a continuous function around the limit, in other words, the value we are approaching is not a point of discontinuity. Okay? So we need to consider what for this function?
What would make it 0?
Okay, what would make what 0?
The denominator.
The denominator, all right? And here we're thinking in terms of domain, right? We're thinking in terms of domain. So in this case here, our domain, if I let x equal 1, that would make the denominator 0. Okay? What else, what other limitation is there on our domain?
Square.
The square root.
Root, sorry.
Okay. So what kind of limitation does that put on x?
X is not 0. Right.
We could take the square root of 0. What can't we take the square root of?
Negative 1.
Okay. Yeah, to stay in the real numbers, we're not going to take the square root of a negative, all right? So we would say that x does not equal 1, but also x has to be greater than or equal to 0. Okay? Now, I have two basic areas of discontinuity here. We have an endpoint at x equals 0, but we also have this point of discontinuity at 1. So what's going on at 5?
Isn't it still continuous at 5?
Yeah, it's going to be continuous at 5. So, how would I find my limit?
Plug it in.
Yeah, plug in 5. Okay?
So if it's not if it's not the endpoint and if it's not the point of discontinuity, then we can plug it in.
Yeah. Yeah, we can now just plug in 5, square root of 5 over the square root of 5 minus 1, and evaluate that, and you'd get your result. Okay? So sometimes things look a little complicated, but once you delve into it a little bit, depending on what value x is approaching, you'll find that, oh, I actually can just evaluate that one. Okay, so that's the limit of a sum. The limit of a sum is the sum of the limits. It's an easy way to remember it, okay? The limit of a sum is the sum of the limits. Alright, so now here's another one. We have products. And for some reason when I exported this, it put these blue dots in here occasionally, so you can ignore that. That's a minus sign. Okay? The limit of a product is the product of the limits. Okay? So I have this here, and this is a pretty obvious one. You recognize that if I were to multiply this together, I'd have a cubic function, so I can just evaluate this, all right? But I also could rewrite this as two separate limits multiplied together, okay? Times the limit as x approaches 5 of x minus 7. Okay? So you plug that in, you get 27 times the negative 2. So we get a negative 54. Okay? Now again, that's a pretty simplistic example there, but that's the same principle that we would use, say, to do this one. Let's say we wanted to do the limit as x approaches 5 pi over 3 of, let's say we had the cosecant x times cosine of x. Okay? Now, I have absolutely no idea what this function looks like. Cosecant times cosine. I don't know what that looks like. But, to find the limit, I can do this. I can say, okay, the limit as x approaches 5 pi over 3 of the cosecant, which is 1 over sine, right? Okay, so I'll go ahead and write that, 1 over sine x. And I'm going to multiply that by the limit as x approaches 5 pi over 3 of cosine of x. Alright? Now, here's where you need to use some of your trig, because you all remember all of that stuff. Okay? And we think about sine. Sine was 0 at 0 and 180, right? So that's where, when I do 1 over sine, that's where I'm going to have asymptotes. Alright? So am I continuous around 5 pi over 3?
Yes.
Yeah. Because it's going to be 0 and pi, 2 pi, 3 pi, 4 pi, 5 pi, where I have my asymptotes. But in between those, it'll be continuous. Alright, so what is the sine of 5 pi over 3? You know what the sine of pi over 3 is?
Was it like 300? It's something. It's in like
5 pi. What is that, sir?
Radians?
Pi over 3 is the same as 60, right? 5 pi over 3 is third quadrant, 60-degree reference angle.
Oh, wait, times 5 is 300. 120?
No, it's
No.
250.
It's 300
Okay.
degrees, right?
We don't need the angle, we need the sine of the angle, right? So it's either a half or root 3 over 2.
Root 3 over 2.
Okay. And
Yeah.
it's in the third quadrant, so sine is
Negative.
negative. So, okay, so this is 1 over a negative root 3 over 2, right?
We don't write the limit anymore?
No, because the limit, we said this was...
Oh, right.
This was continuous, so the limit is simply this evaluated at 5 pi over 3.
For questions like these, are we gonna get our calculator on these? Or do we need to like memorize the units?
Honestly, if it involves the unit circle, they could throw this on the no calculator part. Okay? So you got to know your unit circle. That's just... But we'll do practice with that as it comes up. And we're going to be doing more as we do calculus. Trig comes up in calculus all the time, so you're gonna be using the unit circle as we go forward. So, all right, now cosine we also know is continuous at 5 pi over 3, and in the third quadrant, is cosine positive or negative?
negative.
It's negative, yeah, because remember, all students take calculus. Tangent is the positive one in the third quadrant. So what's cosine of 5 pi over 3? Good, it's the negative 1/2. Alright, so now we have a negative 2 over root 3 times a negative 1/2. So that's just 1 over root 3, or root 3 over 3. So the limit, see what we're able to do here? The limit of this function that we have no idea what it looks like, as x approaches 5 pi over 3 equals root 3 over 3. Okay? Any questions? Okay? All right. So, listen, this is what's really cool about calculus. Calculus is when we really start putting together, we start doing it in trig, but really with calculus, we really start tying together a lot of those things from algebra and geometry and trig, algebra 2, all these other things that we've learned. We start putting them all together and they start making sense. They start becoming more useful. All right, so that's one of the cool things about calculus. All right, one other thing here. You'll notice I gave you another example. This is obviously not a product, it's a quotient. But remember, all division problems are simply multiplication problems in disguise, right? This is just the limit as x approaches 5 of x squared plus 2 times 1 over the square root of x plus 3, right? It's just multiplying by the reciprocal. That's actually what the definition of division is. It's multiplying by the reciprocal of something. Okay? So, now we have two things that are continuous around 5. Alright? So I can evaluate the one and get 27. And I can evaluate the other one and I'd have 1 over square root of 8. So it'd be 27 over root 8.
Mr. Hickson, couldn't we just plug in the 5 into original formula?
Yeah,
Okay.
yeah. And that's what I was saying here. These theorems, in a way, they're so simple, okay? But you've got to know them because this is stuff that you're going to be doing in your head as you're evaluating these, okay? You're going to be thinking, okay, I have this messy looking function. I can really just think of the numerator and the denominator separately, see if both of those will evaluate, and if so, I can evaluate the whole thing, okay? All of that's going on up in your mind. You know, here we're just writing it down so that you can see it.
How do you want us to write the answer? 27 over square root of 8 or the 9 divided by 5? Is it this?
You could either do it as a decimal to 2 sig fig or 3 sig figs, or like here, 27 root 8 over 8.
Pick a main.
Which is, I guess, actually, we should probably simplify that root 8 first. Or I guess we'll just do it now. That's a 2 root 2, and the 2 will cancel with the 8 on the bottom, so it would be 27 root 2 over 4.
But it can be a decimal.
Okay, you can do it as a decimal if you've got your calculator for that. Okay. All right, now, building off of that, there is actually a rule, since it is so easy to tie division with multiplication. The limit of a rational function is the quotient of the two limits as long as the denominator does not equal 0. Again, look for a point of discontinuity, and as long as we're not approaching that point of discontinuity, we're okay. Alright, so for example, in this case, our domain is x cannot be what? X can't be negative 2, right? So, can I just evaluate this one?
Yeah.
Yeah, okay. I have 9 plus 6 is 15 minus 5 is 10. So I have 10 over 5, and I just get the limit to be 2. Okay. Where it gets a little more complicated is down here. And I want to look at two different ways of doing this. Okay? What do I get if I try to evaluate this one?
0.
I get what?
0.
Undefined.
I get 0 over
0.
0, which is undefined, right? Now, you guys who have had some calculus, what's that called? 0 over 0?
Bobo button?
No.
I forget.
What? There was a name for that. When you get 0 over 0, it was a type of a form.
Do you know Ms. Barheim actually tells us?
She does tell you this.
Did you tell us?
I think I told you last year.
Bakash? Do you remember?
Nah.
No?
It's about you, Nacho.
Oh, no. I did not understand anything in that class.
Oh, no.
Independent.
No.
Indeterminate.
There we are, indeterminate.
I've never heard that in my life.
Nah.
No, I vaguely do remember you saying that last year.
Indeterminate form.
Congrats, Sam, not everyone knows.
Okay.
Thanks, Chelsea.
That means it's in a form where we are not able to determine what the limit is as it is right here, okay? However, there is a way we can handle this, and this is where I want to show you kind of two ways of doing this. And the one way kind of takes something you learned back in Algebra 1 and adapts it in a way that'll kind of blow your mind a little bit, all right? So we'll do a little aside here, and we'll do some factoring, okay? How would you factor that?
X plus 3, x minus 3.
All right, good. X plus 3, x minus 3, right? And you have, what if you had this?
X plus 4, x minus 4. I'm just waiting for like the trick.
I know.
We're getting there. It's not a trick, it's just a new application.
Why would you do that to us?
All right? Now, what if I gave you this?
Sam, in there.
Is it?
Oh.
Wait, what does that even mean?
7 times 1, x plus 1 times
Oh,
7
7.
plus 4. What it means? X plus 1 times
No,
x
because
plus-
then you'd have those in terms of like the middle ones though.
Don't you have to write like, yeah, x minus 6 times x?
No, you
plus
can't,
one.
that's impossible. It's a trick question.
The
Yeah.
x plus the square root of
Is it
7.
like, yeah.
Wait, Jesse?
X plus the square root of 7 times x minus the square root of 7?
Yeah, where'd the 3 and the 4 come in the first one? It was the square root of 9, square root of 16, right? So, guess what? We can factor it into x plus root 7, x minus root 7.
Myself.
So it's a prank.
Okay? It's the same principle. It's just the problem is back in Algebra 1, we always gave you the difference of two perfect squares. So we were always giving you 9 or 16 or 25, something that came out to an integer. The fact of the matter is, though, the property still holds even if it's not a perfect square. Okay? So if I had x squared minus 5, what would that factor into?
X plus the square root of 5 times x minus the square root of 5.
Yeah. Okay? You guys get this?
Yes.
Alright, we haven't even gotten to the fun part yet.
Oh, wow.
Okay?
Wow.
We're so lucky.
We're getting there. 2 more steps.
I don't know if that means like it's not fun or
It's even
it's actually-
trickier.
No, it is.
Now, watch. What if I gave you x squared plus 5?
It's
It's
x plus the square root of 5.
Times
That's
x
the
plus.
first one.
No,
And
because
then-
that would be. You can't do that because we have the ones in the middle.
oh no.
Wait, we do have to do the same sign, right?
No,
No,
it's
here,
it's
tap
x. It's x plus negative square root of 5
Oh, wait.
twice.
Actually, no.
Ooh, you're getting there. You're getting there.
Root
Hot.
Okay?
It's so sad.
Was one of them right?
No.
How could I rewrite this as x squared minus something?
Negative 5.
Negative 5 plus
Oh. So it's. Wait.
What?
Oh
Wait.
my god, wait.
Do you agree with that?
Yeah,
So it's
sure, but continue.
X
So
plus. Wait.
10. X
X plus the
minus
square root
plus
of negative 5
Same
times
thing,
x
plus
x
minus the
plus
square
root
root
of
of
negative
negative 5.
5.
Negative?
Sam, go home.
Wait, I don't get it.
Let's
Just give up.
And then
How did we get the 3 and the 4 in the first two?
You square
We
root-
square rooted. So, but you have to have subtraction. So if we rewrite this as a subtraction problem, it's x squared minus a negative 5,
You
right?
can't take square roots of negative
Yeah.
numbers.
Well, you can because you get what?
Imaginary.
Imaginary numbers.
Oh, yeah.
Oh, great.
X plus I root 5, x minus I root 5. Now, the nice thing for you guys here is that when we're dealing with limits and derivatives and stuff, we're talking about things that we want to graph and apply. So we usually stay within the real number system. Okay? So the nice thing for you is you probably won't run into this kind of thing. However, let's go back to one that has subtraction and even a perfect square, but what if it had this?
That's the answer. Just keep it as that.
We can factor this.
X minus
The
4.
square root of x plus 4.
Wow,
The
Sam.
square root of x minus 4.
You're so smart.
See that?
Wait, what? No. Stop.
And just I saw Mr. Hicks's use of
Okay.
so simple and decided to say
You see that?
I get it.
How did we get the x's from the x squared?
square.
We square rooted it, right? How did we get the 3 from the 9? We square rooted it,
Why is it
okay?
So if we just square root of q, that's what we do, okay? Is that what you're trying to say, Master?
Not exactly, okay?
I was like, whoa, that's so cool.
But here's the deal. You can actually factor any binomial that's being subtracted. Well, actually, even if it's not subtracted, make it be subtracted. Okay? You can factor anything using this conjugate thing, all right, as long as you keep the principle the same. The binomials were made by taking the square roots of the two terms in your original binomial, and then you just made them conjugates of each other. Okay? Now, let's take that and step over here to our indeterminate form.
Oh, okay.
What can we do on our numerator?
You can square
Square root of
X.
x
Minus
plus
6.
6, or square root of x minus.
and then you cross out this x square root of x minus 6. That's a whole
Oh my god.
9.
Oh my god.
Yes, there is a hole. When you get an indeterminate form, that just means that there's a hole in your graph at that value of x.
Why didn't you tell us?
I did tell you.
He just did.
Alright, so look, now all we have to do is take the limit as x approaches 36 of the square root of x plus 6. And that we can just evaluate. Square root of 36 is 6, 6 plus 6 is 12. Okay?
So what do you do about that hole?
Well, the hole is actually the point 3612. But what's happening is on the graph, I'll show you what this function actually would look like.
Oh, the point is somewhere else.
What this graph actually looks like is this. We have this, and then it's a radical function, so it looks like this. However, over here when x is 36, y is 12, and there is a hole in the graph. Okay?
So is that the limit?
So right there, there's a point, 3612, where our graph has a hole, but remember what we said yesterday when we were looking at limits. Does the function have to be defined at the point?
No.
No.
Approach it from both sides.
Approach. Remember that word approach. It's approaching 12 from the left, and it's approaching 12 from the right. So the limit equals 12, even though the function has a hole at that point. Okay? It's kind of cool stuff, all right? Now, one thing I will tell you, a lot of people don't necessarily do it this way, by factoring, okay? Because it's so ingrained in our minds that, oh, when there's just an x to the first, we can't factor, all right? You can, all right? But let me show you what is kind of more the traditional way of doing this. Actually, I don't want to get rid of all that.
The k substitution, like does that relate?
I'm not sure what you're talking
Like
about.
where you were, I don't know, Muskoka did this thing where if it was like x cubed plus something over x to the 6th, which is like x cubed equals k, and then you solve for k, which
What are
consequently
you
solve for
saying?
x.
Oh, I get what you're saying. That's not the same thing here. Actually, what we're going to use here is the conjugate of our denominator. Okay? So if you look here, what we could have done rather than factoring the numerator, is we could have taken x minus 36 over root 6 minus 6, or root x minus 6, and multiply it by the conjugate, so we rationalize the denominator. Okay, this will get rid of any radicals in the denominator. But we'll do more of this next week after you're done with your test. But notice, what does the denominator FOIL out to?
X plus 30 minus 36.
Yeah. And then the numerator is x minus 36 times root x plus 6. Okay? And now those cancel out. You're still left with the same thing we were left with down here. Okay? We just got there a little bit different way. This is traditionally the way that is taught. Probably like showing you both because it's kind of cool.
Do we have to write out the whole, like when we're doing this problem?
Oh, identify what the whole is? No, I'm just showing you why the limit exists even though it's not defined at that point.
Thanks, Sebastian.
Alright, so that's our limit of a rational function, okay? Last thing here, this is, we can take a breath here. This one is another easier one, okay? If we have a function that's raised to a power, we can simply take the limit of the function and then raise that limit to a power, okay? So the limit of a power is the power of the limit, okay? So here, I don't need to cube this x squared minus 21 first. I can instead take the limit as x approaches 5 of just the x squared minus 21, and then that result I will cube at the end. Okay? So what's the limit as x approaches 5 of x squared minus 21?
Wouldn't you take that 3 and put it in front?
You're thinking of logarithms.
Oh.
Yeah. What'd you get, Isabella?
4.
Yeah, 4. 5 squared is 25 minus 21 is 4. So I just take 4 cubed.
And that's the answer, right?
And that's your answer, okay? 64. Okay? And this applies, if we go back to trig again, you know, I could do, what's the limit as x approaches pi over 6 of, you know, sine to the 5th x. Alright? Well, I could rewrite that as the limit as x approaches pi over 6 of sine of x, and then raise that to the 5th power.
Oh, we can do it too.
Okay? Because I know sine is continuous for all real numbers. What's the sine of pi over 6?
Can I look it up or do I have to guess?
Same as sine over
Oh, yeah. Root 2. Or 1/2.
1/2.
Yeah, yeah.
This is the same, pi over 6 is the same as 30, sine of 30 is a half. Okay? So now I just know that this is 1/2 to the 5th power. So now I just have to do 2, 4, 8, 16, 32. Alright, so it's 1 over 32. And there's our answer. Okay? So I don't need to know what sine to the 5th looks like on the graph.
But definitely need to know the units.
Okay, but we definitely need to know your unit circle. Okay? Alright, so those are our basic limit theorems. And these are things, like I've said a couple of times, these are things that a lot of times you're just going to be doing in your head, like the limit of a sum. I don't expect you to write that as 4 or 5 different limits, but in your head you know that you can just handle them one piece at a time. Okay? So, alright.